Hello everyone, Gabe here from the Uplay team here at Massive, and welcome back to another episode of Beyond FPS. And again, I am joined by...
So my name is Oliver Voge, and I am a senior programmer here at Massive.
So last time out, we talked about how CPUs function at kind of their basic level.
And today, the main focus is how do we give the CPU the actual data to process?
Nice, let's get to it. So, where are we starting?
So last time, the big thing that we took away was that code that we will run on the CPU is data, and also the data is data. So it's all data and it's basically all the same. So what we want to do is we would like to load up the data into RAM and then execute the RAM.
How are we going to do that?
So right here in front of us, we have a simple 8-bit assembler simulator. And if you would like to play with this, the link is in the description. So what we have here in our hands is a place where we can write very simple code. We have the actual CPU part here, and the CPU has 4 what is called registers. So a register can just hold a number. And since this is an 8-bit simulator, that means that we have 8 slots of zeros and ones we can deal with. The biggest number we can deal with is 255. We have a thing called an instruction pointer. You'll see what that does in a bit. We have a stack pointer. I'm not going to go into what that is in this episode. We will work without the stack. That's something we can talk about later. And then we have 3 flags, and we'll only deal with the 2 over here. So we have a 0 flag. That goes from false to true if the last instruction given to the CPU resulted in the number 0. Like if you would add 2 numbers together, but you were adding 0 plus 0, the result is 0. Or if you took 2 numbers, like 5 and 5, and you subtracted them from each other, the result is 0. And then the other one, C, is carry. And that just means, was there any left over? So we have those 4 registers and the instruction pointer, and then we have those 2 carry flags. And then here below, we have the RAM. And RAM is basically just a list of numbers.
What are all those zeros? I assume those are zeros.
Yes,
right?
these are all zeros. So that means that there's nothing in our RAM.
Okay.
Our RAM is completely empty, and we would like to load something into the RAM.
But so, when I think RAM, I'm thinking 8 gigs, 16 gigs, 32 gigs.
Yeah.
What is the size of this RAM that I'm looking at now?
Not much.
Okay, not much.
We have 255 addresses. So it's not even a kilobyte.
Oh, okay, cool.
Yeah,
Nice RAM.
It's very small. And this is a simulation of a computer, so everything will be at the same speed. But normally when you're executing something or you're loading from RAM, there is like speed differences there, but we're not going to go into that as well. The clock speed that we have is 1 hertz.
Nice.
Which is once a second, and it can go all the way up to 16 hertz.
Okay.
It's quite
good stuff.
Good stuff. So let's start with some simple instructions. Like we talked about last time, we have an opcode. So it's what is the operation we would like to perform. And then what is the A and the B, if we think of it that way, that we would like to perform the operation on. So if we write add, and then A and 5, what's happening is you're asking for the opcode add, whatever the operation code is for add on the CPU. We would like to store the information in A. And what is the information we would like to store? It's 5.
So when I think of code, I mean, we did code in school.
Yep.
Is this a language? What is it we're writing right now? Is this some sort of specific language, or
yes.
what is this?
This is a language. The language is usually called assembly. The assembly is usually named after the CPU. This isn't an actual CPU, so we can just call this assembly. If you're writing towards a regular like Intel or AMD processor, it would be called an x86 assembly, or sometimes an Intel assembly or that. And if we assemble this, you'll see that in our RAM, we have now some data.
We have 13 and a 5.
Well, we have 13, 0, and 5.
Okay.
So 13 in this language is add. Then we have A, which is the first register or the 0th register, and then the number 5. Like if we change this to a B, which is the second register, we have a 13, 1, and 5. So what will happen is when we run this, is the CPU will look at the first, because that's where we are in the instruction pointer, look at the first bit of data, which is actually code. It will pass that to the decoder and say, what is 13? The decoder will say, that is add. Okay, if we want to add something, we need the next two things. The next two things are then 1 and 5. Then into register 1, which is B, we'll put 5, or we'll add whatever is in 1 and put 5 there. So if we hit run, 1 second later, because we are at 1 hertz, we'll see that B has a 5.
So if this is, I'm thinking in like a program sense, who is sending the add B5 and who is receiving the now value of B, which is 5?
So who is sending it is, there's nobody directly sending it. We just loaded that data or that bit of code into RAM.
Why would we need to load that bit of code?
Because when the CPU or whoever is the control unit for the CPU would like to run some code or run some, basically run some data, if you think of it that way, it would look at RAM and say, okay, what's the thing I need to load? Or what's the thing I need to execute? Let's fetch that, let's decode it and send it off. So when you're writing a program, what we're basically writing is, you're usually writing a higher level language than assembly. You're writing in C or C++ or any other language. That when you've done writing the code, you compile it down. And when you're compiling it down is into a series of these kinds of instructions. So division.exe is just a bunch of instructions like this, just very carefully arranged in a very careful order. The data that it wants to load is either in the executable file or it is in some other file. And if it's in some other file, then that file is then also loaded into RAM. So if we play with this a little bit more, let's say add B, then 7. If we assemble this, you'll see that we have 13, 1, 5. That is the first add instruction. And then we have 13, 1, 7.
Yeah.
So into register 1, we want to add 5. And into register 1, we want to add 7. So it's because we have the add instruction. So once a second, we have 5, then we have 12. So if we keep doing this, let's add a few more of these.
Math.
Exactly. 8, 9, and 10. If we assemble, then we can see that we have a series of instructions in our CPU or in our RAM, because we assembled it and loaded it. We can hit run, and then once a second, B will increment slowly. We're up to 45 right now, and we can actually increase the clock speed.
Make it real quick.
Good reset, and then assemble and hit run.
Bam.
Bam,
Done.
much faster. You can also watch the instruction pointer. It starts at 0, will then go to 0, 1, 2, 3, and then 4, 5, 6. So 3, 6, and we'll jump at 3, because using the add instruction, it knows that the next two things are data. So we'll jump to the next one, which it's assuming is also an instruction.
What if it's not?
Yeah, what if it's not? Then you could just be running some garbled mess and your computer might crash. So in the instruction pointer, we have a 3, 6, 9, etc.
So when we're talking about an actual RAM, so you talk about this is like 1 kilobyte.
Yeah. Oh, not
How many sets of instructions are there in 16 gigs of RAM? How many?
Way too many.
Way too many.
It's so many you can load into that. So this is one thing we can do. The next thing is we can play with RAM, and we can just put stuff into RAM. So if I go and say we would like to move into A, the number 32. And move is just copy, so it will overwrite whatever in there. So if we assemble it, we'll see the instructions. Move is then 6. We run it, and now we have 32 in A. But this 32 is not the number 32. Well, now it is the number 32, but we would like to treat it as something else later. So in the next line, we're going to say move or Swedish keyboard. So move the number 255, and then we have this bracket around A. And what that means is we don't want to move into A, we want to move into the place in memory that A is referring to, which would then be 32, right? So if we assemble this and do a step 1, we get 32 in A. Then we will move 255 into whatever A is pointing to. And this is a pointer, basically. So if we do a step here, we will see 255 out here.
Why is it down there?
Because this is the 32nd
okay.
memory address. We can then say INC on A, increment the A, and then copy this, and we can move the number 64. So if we assemble this and step, so we have 32 in A. We copied the 255 here. We increment A by 1, so it's now 33. And then we step again, and now we have 64. So we wrote a program that can write data into any location in memory. It's not a big program, it's not a very complicated program, but it is a program nonetheless. So if you think of your keyboard or your mouse or any sort of peripheral device as a bit of software, which is then just a series of instructions in RAM, it is then being executed by your CPU. And every time you move your mouse or you press a button on the keyboard, a very specific memory location is changed. And then the program that you can think of it as two different programs. One is the program that is listening to the mouse, listening to the keyboard, and writing that information to that specific memory location. And then there's another program, which is usually the operating system, that is looking at those memory locations and seeing, has there anything changed with the mouse? Is there anything new with the keyboard?
So my mouse movements is a set of instructions that is going through RAM and doing this process in a more complicated way.
Yeah.
But this is basically just a simplified, if I want to move my mouse around,
Yep.
it's basically telling it these kind of instructions are being sent. And your CPU is processing these to understand actually what is being shown on screen, which is the mouse movement.
Yeah.
So I know things are fast, but that sounds like a lot of stuff that's happening. Why is there no perceivable delay in moving my mouse?
So you would think that like we're moving the mouse, it looks very smooth. We're moving it a few hundred pixels over here and it looks fine. But your computer is running at 2, 3, 4 gigahertz or whatever the frequency is, which is in the billions of instructions a second. And you have multiple cores. So when you move the mouse, you may be only doing that on one of the cores.
So moving a mouse like halfway across your screen is like a couple hundred instructions maybe, or what?
Let's say a couple hundred, even if it's a couple of thousand instructions, in the relative scope of a processor that is doing billions of instructions a second per core.
It's basically nothing.
It's basically nothing.
It's completely irrelevant.
You can imagine on like a smaller computer or a slower computer that mouse movement could impact things, but you'd have to dial down the clock rate quite a bit actually. So a lot of software is dealing with taking memory and writing it, or taking data and writing it into memory. So as another quick example, let's make a loop. Let's make a thing that runs for quite a while. You can see that this gray area down here, what this is the output over here. And what we're going to do is I'll indent this and you'll see why in a bit. I'm going to move into A, the number 4. And then I'm going to move into D, the number 232. So the stack pointer is at 231. That's this order thing there, here. That means that this one, which is the first one in output, is 232.
So what is output?
It's this screen over here. You'll see what will happen. I can actually write data to this little screen.
What would output be normally if it's a sense of your real PC? What is technically output?
It could be command line.
Okay.
So you have output, you can write text there. And this could also be just pixels, if it's small enough. Usually that's not how that is implemented, but it could be. That absolutely could be. So we're into A, we're moving the number 4. Into D, we're moving the number 232. That's just to know where this one is. And then I'll create a label, call it loop. And I'm going to increment A, so A is going to be 5. I'm going to move into where D is pointing, which is then the 232nd location in memory. I'm going to move into it, A, and then I'm going to jump to loop.
Which is basically telling you to go back.
Yes, go back up. Loop is a label. So if we assemble this and scroll down a little bit, we have a label called loop, which is at address number 6. So it's at the 6th instruction pointer. So we can assemble it, we can step. So we have 4 in A, instruction pointer is at 3, and then we step 1 more. Now we're at 6, which is where the loop is. We're going to increment A will go to 5. We're going to move A into whatever D is pointing to. We'll get a garbled mess up here.
It's a square.
It's a square. And then we will jump back up to what loop is, which is the increment A. We will step, move whatever is in A into D, still a garbled mess, and then keep on jumping up to loop. And we can actually run this. And we can, let's do a stop, assemble, change the clock rate to 16, and run this. You can see it's moving up and down, up and down. But after a while, because A is now 30 and then 40, you'll see that the characters are changing into letters and symbols, and here you have the alphabet. And then you'll have the lowercase alphabet.
Why was it a garbled mess to start with?
So this is called ASCII.
Ah.
So there is an internal table called the ASCII table, which is from 0 to 128.
Ah, garbled mess again.
Garbled mess again. We'll go a little bit higher. We'll get little special characters.
Basically just typing all the characters your PC recognizes, I guess, maybe?
Some of them.
Okay.
There's another standard called Unicode, which has a lot of, basically more characters. So it is PC dependent. So if you're running this on your PC, we're back to garbled mess. But we now looped around.
Yeah. So what in this loop? So this is in the sense of my PC functioning all the time.
Yep.
What is this an example that's maybe not close up, but a very basic example of?
So a lot of software out there is, because it's running in a loop. A game is running in a loop again and again. It is reading the input from the user. It is updating any kind of AI or data or stats or bullets flying in the air. And then it is taking all that data that it knows where it is in memory and then sending that off to the graphics card. And then we are back to reading the inputs from the user.
And this is happening how many times a second?
It depends on how fast your CPU is. Sometimes games are limited down because we want to run them at a stable 60 FPS. So we would like the loop to not go too fast or go at a very specific rate. Or we might actually do calculations to say, we did the loop, we did the update, how long did it take us? Okay, we have this amount of milliseconds left, let's wait, or let's process something else until we're done. So
if your CPU basically isn't able to run this loop fast enough, is that considered like a CPU bottleneck?
Yeah, if you want stuff to happen faster, and the list of instructions that you have to go through and read from memory and do all this processing is long enough, then and your CPU isn't fast enough, then you will have a bottleneck of like you can't go through this loop and you go back up. So you were too late on sending the data to the graphics card or sending the data to wherever you want to send the data. So the graphics card got the data too late, so you might see a stutter or you might see like duplicate frames or whatever's happening. And this is only one CPU, and then you can have multiple CPUs that they're working on things together. They might share RAM, so then you have to think about what if you're writing to RAM and the other one is reading from RAM, and then you might have like problems of them colliding with each other. So there's all sorts of problems there.
So what's your few seconds recap of what we just looked at?
So in the first episode, we talked about that the CPU is some sort of logic units or arithmetic units that will take in an operation code, take in some data, and then we'll process it and then write that data out to some memory location. And in this episode, we looked at where we could assemble together a series of these operations where we have the operation code, the data, and the memory. Then we can take that assembled information, we can load it up into RAM, and then we basically execute RAM to create a beautiful loop like this.
Awesome. The moral of the story is download more RAM. Thank you for watching, everyone. We hope you learned something. As always, if you have any questions, please leave them in the comment section below and we'll do our best to get back to you. But our CPU adventures don't stop here, and we'll be back next month. So until next time, bye.